Mr. Miller. I started called physics here, and we want to continue looking at charged particles and electric fields and such things. But here's a little question for you. So we've already determined that we know how to deduce what that net electric field is in the vicinity of a bunch of point charges or for some continuous charge distribution. So then what happens if we place another point charge in that electric field? Well, we already say there's an electric field force exerted on it, which is just QE. Well, what if that is the only force exerted on it? The electric field force. What then? And this is where some nice notions come into play. If the only force exerted on a charge is due to the electric field in which it resides, the electric field force then constitutes the net force. What do we know about the net force? That's right, net force produces the acceleration of the mass. So this is what we've got going on. We've got some net electric field at the location of a point charge. So consider a point charge. Q1 in an electric field E hat at its location. The electric field force exerted on that charge, let's just write F sub Q, is going to be equal to Q times E hat. We've already dealt with this. There's the electric field force on the charge Q. Well, if F sub Q substantiates the net force on the charge Q, then sigma F sub Q produces the acceleration of the mass of the charged particle as such. Net force on the charge Q produces the acceleration of the mass of charge Q. So what can we do? We can kind of put this together. F sub Q is equal to QE hat, right? So this we can write as QE hat is equal to M sub Q A hat. So if we wanted to figure out the acceleration of the mass of that charged particle Q, the acceleration is going to be equal to the charge multiplied by the electric field at the location of the charge divided by the mass of the charge. And that's very nice to be able to deduce. Hey, if we know that we put a charged particle in an electric field, and the electric field is the only thing exerting a force on it, that charge will undergo some sort of acceleration, be subject to an acceleration due to the net force that's acting on it, and will thus inevitably start changing its motion, right? There we go, pretty cool, right? So this brings us to some things that are of interest, like, hey, if E hat is equal to a uniform electric field, constant magnitude and direction, we will have that sigma f hat sub q will be equal to a constant, and thus a hat will be equal to a constant. And we already know what happens if the acceleration of an object's constant. We have equation of motion for constant acceleration, right? Well, yeah. If we're dealing with the x direction, or just really any direction, let's just say the r hat direction, we'd have things like, now delta r hat is equal to 1/2 a t squared plus vi times t. We have that v final is equal to at plus v initial. We can have that v final squared is equal to v initial squared plus 2a delta r. We don't need to put a hat there because this would be implied that these are vector quantities here. But there we go. We got equation of motion for constant acceleration. Whoosh! Fantastic. All that we need to know is what is its initial velocity and what is the acceleration. The acceleration, again, is this right here. It has a direction that actually is aligned with the electric field. It can be positive or negative, though, with respect to the direction of the electric field. A negative charge will want to move in the opposite direction of the electric field. That is the direction of its acceleration. A positive charge has its acceleration in the same direction as the electric field. That goes with the force, right? Force on a charged particle in an electric field. So this is important, it's nice, but it does, utilizing this, restrict us to dealing with uniform electric fields, constant magnitude, constant direction. While all the electric fields that we've looked at so far, none of them are constant. The electric field due to a point charge varies spatially. The further you get away from it, the less the field strength is. Even a line segment, continuous line, as you get further away from an end of it, hey, the field drops off as 1 over a. From the midpoint, you get further away from it, the field drops off as 1 over a. So we have variance, but that's okay. We could still have variance. That would just mean that the acceleration itself varies with respect to how the electric field strength varies. And that's still stuff that's doable. This is really important. This is for a specific case. But this is nice too because it turns out that we can produce uniform electric fields over small distances and produce this sort of constant acceleration. And we will do some stuff like that as time proceeds onward. So, yeah, we'll just kind of leave it at that. Pretty simple to deal with. Acceleration, some old stuff that we've dealt with in previous semesters, and pretty cool. All right. That's it. Have a good one. Until next.